Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new mini-series on measurements with the secrets of a level product and process. This is a continuation of Web 201.71a and b, so it may be best to see them first if you have not already done so. I know your time is precious, so let's get started. Recall from the last clip the Roysum rule of instrumentation that says, the more expensive it is, the less I trust it. There we also gave the corollary that I don't even necessarily trust a tape measure, and went on to demonstrate why that instrument might not be adequate for its most common use, checking web width. Here we will add another corollary. I also don't trust T-squares all the time. This one is also based on personal experience. One of my 5 helmeted hobbies was designing, building, flying, and eventually crashing an experimental aircraft. You can find the details in my Web 301.07 clip. In any case, I needed a really good carpenter T-square to build my airplane. I bought no less than 6 name brand squares of different makes and models. None was square, as can be demonstrated by a simple test. Troubleshooters and instrumentation people alike should know tricks like this to check their work. In any case, before giving up, I checked my wife's sewing square, and it was dead on accurate, as can be checked below, and I built my entire airplane using it. So you should be seeing a pattern here. That is, do not trust instruments for important work without first checking them thoroughly and rechecking them regularly. This is true of simple tools, and is even much more so for expensive tools, such as web thickness profile scanners that are ubiquitous in paper mills, film extrusion plants, and many more places. So, let us put this $1 million thickness profile measurement tool to the practical test. Here is a wound roll with a baggy web complaint. Those who want to know more about baggy webs will find almost anything they wish to know about troubleshooting this most common defect in my Web 201.45a through r series of clips. In any case, we need to check out root cause mechanics so that we can either reduce the root cause of the problem or cull rolls that are too bad before they are shipped or run. Here is a roll where we can see a bulge corresponding to the location of the baggy lane. Our eyes are incredibly sensitive. With training and under good conditions, we can see an error in a smooth cylindrical surface as small as the thickness of a human hair. We can also feel a bulge corresponding to the location of the baggy lane. Our hands are incredibly sensitive. With training and under good conditions, we can feel an error in a smooth cylindrical surface of about the thickness of a human hair. Finally, we may also be able to hear a bulge corresponding to the location of the baggy lane. Those of you who are familiar with roll hardness meters will know exactly what I'm talking about. Everyone else should go to school, such as my award-winning and trademark Web 101 web and winding schools that have been taken by about 5,000 students just like you. Our ears can be incredibly sensitive. With training and under good conditions, with a well-designed stick, we can hear an error in a cylindrical surface of about the thickness of a human hair. it will sound at a higher pitch, and it will read higher on a roll hardness meter at the bulge where the baggy lane is than at locations next to it. However, if you are blessed with the $1 million scanner, you might be tempted to check it out to see if there's anything wrong with the web in that area. However, that is totally unnecessary. We have already verified the location of an error in the web with 3 totally different, independent, and quite sensitive instruments: our eyes, our hands, and our ears. You could even do double-blind tests by asking several of your technicians to find the bump. All should be able to do so. We have now verified web thickness troubles in that lane using 3 independent instruments, double-blind checks, and compatible with winding theory. A scanner at this point is totally redundant for the purpose of indicting the defective web. If you felt you needed more cross-checking than the 3 methods we've already given, you could go to the scanner, perhaps because you paid so much for it and you should probably use it for something. What you may find is a plot of thickness profile that looks like the EKG of a heart patient that's ready to die, full of peaks. The next scan may look substantially or totally different. At this point, cherry picking of data is quite common. You try and find a peak that matches your favorite working theory. No worries. If it doesn't show up on this scan, it might show up on the next scan, which is likely to be different. Alternatively, you might find a profile that looks relatively flat and be tempted to think all is well. However, the wound roll and your customer are already telling you that all is not well. The flat scanner output is just an artifact of scaling. The process engineers decided that all these peaks, which didn't seem to line up with much of anything important, were just a distraction. So they turned down the gain. The final insult comes from QA that is tasked with the protecting of the product and the customer. They put control limits on the display and claim, "But we're in spec." Who cares if you are in spec if the customer is not happy? This common result is because scanners might not reliably see the 1 to 10% thickness variations that would stretch many webs into unacceptable bagginess when wound. At 1% variations, you have few problems, but at 10% variation, you might have few customers. Of course, your mileage may vary, as they say. Sometimes with thick products, you might have more than sufficient resolution with the scanner, or particularly the web test lab, to pick out the root cause variations. With thinner and fussier webs, the trustworthy is less. Of course, I am not suggesting that scanners have no utility. They are certainly much more responsive than looking at wound rolls, perhaps an hour quicker on the results, perhaps allowing you to make corrections so as to not lose yet another roll in the sequence due to profile problems. Also, scanners do, on occasion, see profile troubles that would not reliably make it through any winder, no matter how well designed and how well controlled. Instead, this story is yet another warning to cross-check your conclusions. Perhaps as simple as by asking the winder operators what they think about the quality of the current web profile thickness variation. There are 3 starting points for a more detailed description of thickness profile variations and their effects and their measurements. The first is a 20-year-old paper given at 2 major trade organizations that still resonates today. The second is the must-have 750-page Web Handling Handbook, written by myself, Tim Walker, and Dylan Jones. Last but not least is my award-winning and trademarked Web101 class that has been taken by about 5,000 people just like you. Here you will learn all about what the winder requires of the web and why. Thank you so very much for joining me in this Measurement Miasma mini-series. I hope you've enjoyed the stories. Stay tuned for the next clip where we will discuss how much data might be needed and why having too much or too little or the wrong type is quite common. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.